Okay, well, so today we're going to be thinking about spatial data still, kind of continuing our interest in spatial analyses, but today with the package ADE Habitat HR. And so the first thing to do is install this package. And remember, we want to install packages prior to loading any other packages, as we learned when we tried to install ggvegan after loading ggplot several lectures back. Okay, we're going through the process here of installing ADE Habitat. HR stands for home range. We'll also be using a couple of other packages that are dependent packages, like this dplyr. Okay, looks like that went okay. It restarted R. So hang on, question in the chat. Oh, thanks, Alex, for sharing that. Okay, so let's call a library for dplyr. We'll do the same for ADE Habitat HR. So there's a new version of R out already, 4.05, and there's just a warning message there telling us that these packages were built under this most recent version. And we're going to get another warning related to this as we go through the code today when we start doing some of the spatial analyses. If some of the packages were built under a different version, there's going to be a comment attached to that. And so we're going to get a warning that there's a comment, and that comment's going to be lost when we plot the data. And it's related to this version issue. Okay, so it sounds like a lot of you are picking up on warnings. They're not always failures, although it displays as red text, just like a failure. A warning does not indicate failure, and sometimes it actually means there's nothing wrong with the code. There's just, you know, some interpretation or interpretive caveats that you might keep in mind. Okay, so if everyone was able to install and load ADE Habitat HR, we'll use this dplyr as well. So go ahead and load that one. The first thing that we're going to do is just have a look at some data that comes with this package ADE Habitat HR. So I'm just going to run this, and then we're going to do a question mark on that data to explore what we're really thinking about here. Okay, so this data set is from a Mediterranean region in the south of France that has data related to radio tracking of wild boar, and these were data collected as a part of a PhD thesis in 1996. Okay, so most of the lectures for this class, I try to use data that are already in R so that everyone has access to those data, and you can repeat this analysis on your own. And the main part that we're interested in is this relocations or relokes. And it's an object of class spatial point data frame, which is important for creating that type of data if you want to do some of these analyses of home range. So the data on wild boar are already in that format. In the second half of the lecture today, I'm going to show you how to take just raw XY coordinates and create a spatial points data frame. And that's probably where most of you will be interested in this. You may have your own data on relocations of organisms and you want to think about home range size. So you'll need to go through the process of transforming the data. But for the first introduction part here, we'll just focus on this data set that's already transformed properly, or formatted properly, I should say. Okay, so we're going to create an object called REL, which is just short for relocations. We're going to go into this data set, and and it's a list, by the way. It's a list of two objects. And we're going to focus on this relocation part. So $RELOCS. Okay, and so when we run that, we get an object called REL, and it's the formal class is spatial point data set. And we can look at the headers of that, just the column names, by using the function head on REL. And then if we have a look at this, we've got coordinates there's a coordinate system there. There's a name for each individual. These are wild boar, so they named the radio tagged individual. We know something about the age, the sex, and then individual dates of when relocations occurred. So this would be 1993, the 7th month, the 1st day. Okay. And then we can also run the summary function on REL to learn a little bit more about the nature of the data. And so here, it gives us the minimum and the maximum. Notice that we don't have a projection. I'm going to show you later in the lecture how to define a projection of XY coordinates. It tells us that there's 3 levels of name or 4 levels of names there, and the number of observations or relocations for each of those individuals. And then ages were only 2 and 3, male or female coded as a 1 or a 2. So those you might actually, if you were going to formally analyze those, you might want to change those to a factor. They're currently being interpreted by R as a continuous value, but it's really only an H2 or an H3. Sex is either a 1 or a 2. And then the date is interpreted as continuous, but we know those are actually formatted as individual days. Okay, we're going to focus on the coordinates for each of these 4 individuals for today's lecture. Okay.
Can I interrupt you for a second?
Of course.
Sorry. I loaded everything. It all worked fine. When I did head of relocations, all the values are the same, except that I don't have that coordinates column. I just have name, age, sex, date. So
is it possible that it's on a different row if you scroll up in your R output?
It would be possible, but I don't see it there.
Oh, interesting.
Yeah, it's as if it's as if the relocation data that came over didn't include coordinates. But
when you created REL, did you use the name of the data set $ and then relocs, RELOCS?
Just left what you had there and press run for that.
Oh, that's right. I already typed all this code for you. Interesting.
I think I have the same thing that you do, Alex. I have like the coordinates right below where it says object of class, and then it has like min and max, but it's not in a column next to the name.
Okay.
Oh yeah, and actually when I looked in the like the view version of the data, it says chords. It doesn't have. Oh, no, it does have coordinates. I don't know why that wouldn't come out, but do we need I think we need to open SP, don't we? Or no? For any of this?
The package SP?
Yeah, does that matter? Or is that the whole point is add habitats by itself?
So you should be able to do it with ADE Habitat HR. Maybe, what operating system are you using?
Windows.
Oh, okay, so it's not a display issue. Let's see if the next line of code runs for you. Let's just try. If you don't have coordinates, this is not going to work. But let's try and estimate home range size using this minimum convex polygon, MCP, okay? And we'll do some more troubleshooting for Alex if this doesn't work. So convex polygon, CP, is what we're going to name this. We're going to use the function MCP on this object REL. And then we're going to estimate it based on the first column, which is the name of those 4 individuals, okay? That's the brackets. Remember, everything inside of those square brackets on the right is a column. We're just telling MCP to calculate this minimum convex polygon for each of the individuals that have the same factor level in that first column, okay? If you run that, you should get an output that's called CP, and you can save that as a data frame. And you should see something like this, where it's the ID, and then it's the area of the minimum convex polygon. If you try to run that, Alex, does it work for you?
It does, and I don't know how, but it does.
Okay, we can take a deeper dive if you'd like. It's probably just when you did the header or the head, it may not be showing you all of the data. Is there anyone else that had an issue with getting this, creating this CP object? Addie, did it work for you?
Yes, it did.
Okay. Okay.
I loaded when I loaded the data,
Uh-huh.
it loaded way more than just the Porcupine species list.
Oh, okay.
So I cleared the environment and then I did it again, and it showed, now it did what you did, but the first time it was like kind of crazy.
Oh, interesting. Were you starting a brand new R? Was your environment empty and no packages loaded when you started?
Yeah, everything seemed normal, but I just noticed that was kind of strange. So then I just cleared it and did it again, and it was fine.
Okay. Yeah, it should be the Cuchabon. It's French. I don't speak French. And then SP is for the spatial. It's a spatial data set. Yeah, that's strange, Natalie. I'm not sure, but it seems to be working okay now.
Yeah, it's working fine. I actually have a question about this minimum convex polygon.
Okay.
I'm kind of confused. The coordinates, well, I think I have a question before that question.
Okay.
This CP or the REL, what kind of, is that a data frame that the object is in, or that the data is in, or how? Because when I click on that, I don't see like the raw data like we do when we do a matrix or something.
Okay, so it's probably stored as a list, and when you look at a list versus a data frame, it stores it much differently. Remember when we were first talking about data structures, a data frame, there's an observation for every column, but you can store items of different dimensions together as a list. And looking at summary information from a list is a little more complex than just looking at a data frame of a number of columns by a two-dimensional data set, essentially, right?
Yeah. So I guess my question is, how did you know that the coordinates were in, or how would we know that the coordinates are in the first column of the list, or like the first?
So are you talking, so you're able to make REL based on relocations, right?
Yeah.
And when you have a look at REL, if you just type it in, so are you able to do this? I just typed REL into the console, and it shows coordinates and then name and then age, sex, and date. Do you see that same thing?
Yeah.
Okay. So the coordinates are the first column.
Okay.
But notice that they're stored together
Yeah, I see now.
parenthetically.
Okay, thank you. That was
So it's
really
not like an X column and a Y column.
Yeah.
And we're gonna in the next example, we're gonna switch to birds, and we'll start with X, Y data, and then we'll transform it into a data set that matches what we're looking at here.
Okay, cool. That would be awesome.
Okay, maybe I did those backwards. I wanted to give a brief overview of what the package can do.
Yeah.
And then kind of drill down and and kind of show how you might use the package for your own data, right?
May I add one last thing?
Yeah.
I think, I'm not sure if this is what you're getting at, Natalie, but this type of like the class of this is a spatial points data frame. So it's not like your same like regular data frame that you'd use, that you create a matrix with. And so I think that might be why it looks different, but you can see on the side there of the environment, it says like formal class. It's just different from like all the other data sets that we've imported manually.
Yeah, so if you just have a brief view in your environment up here, you can see there's different dimensions for portions of it. I mean, it's a pretty complex data structure, right? Good, Natalie, I see you laughing.
Yes, I just got interrupted.
Oh, okay.
Yeah, that was really helpful.
Okay, so everyone was able to then run the CP. We can set it, when you just do this as.data frame, that's grabbing the output from CP and storing it in a data frame so that it is something that we're more accustomed to seeing, where you have each individual, well, it gives the rows, it tells you the ID again, that information is redundant, and then it tells you the area for that minimum convex polygon. And what it's doing is each of the coordinates in space, it's drawing a polygon that connects each of those around the outside and creating a convex hole that matches the kind of spread of those data. And that might make more sense if we show what this looks like. So this next line of code is just plot this CP, which is the output from the MCP. If we run that, of course, the figure margins are too large, so I'm just going to make that plot window larger. And you can see that it's creating what looks like a polygon, and it's doing that around the actual relocations. And so this next little bit of code, we're using the plot function again. We're plotting REL. Here, the color is going to be set to, we're going to create this as.DataFrame of REL, and we're going to set the color to the first column, which is the name of each of the 4 individuals that we're tracking. And then this add equals true just means instead of creating a new plot, it's going to add that plot to this existing plot that we just created. Okay, so I'm going to run that. And if we zoom in on that, you can now see that each of these cross hatches represents a relocation for each of our 4 individuals. And the minimum convex polygon goes around those. There may be an outlier point every now and then, but it creates a minimum convex polygon that incorporates the core of the data. And it's shaped in a way that it matches kind of the outline or the profile of those data. Okay. For those of you that are using Orty Hole, I know we talked about that last week or whenever when we were looking at creating an ordination for an NMDS. You can do a minimum convex polygon around your groups. It's the same principle. It's just showing basically one way of calculating home range or the area that's used by each of these individuals. Here, using a minimum convex polygon. Okay. The other thing that you can do though is you can look at, you can use this function mcp.area to calculate the size of a home range or the size of that minimum convex polygon against different subsets of the data. Okay, and so this is, we're just going to name this object, and then we're going to use this function mcp.area and on the object that we created, REL, and then in the brackets, we're just going to say we want to make a computation for each of the 4 individuals there. Okay, so if we run this, same problem with the figure margins. Oh, I might have to make it in a new window.
Have you ever done the Windows thing? Oh, there we go.
Yeah, I was thinking I was going to have to do that. Of course, with Zoom, it's always a hassle to get those things to pop up. But yeah, there is a way that Alex was alluding to doing, was it Windows open parentheses? It creates a new plotting window. It doesn't have to put it in that small corner of RStudio. It'll be a new window, and you won't have this problem of the margins being too large. All I did was just resize it for simplicity, and we can zoom in on this. And the idea is for each of the individuals across a subset of the data, 20% of the observations all the way up to 100% of the observations. Here's the size measured by default in hectares of the home range. And as you might expect, as you watch an individual for longer, as you start to accumulate more and more observations, the home range size grows. But notice it grows at a different rate across each of these. And then towards the end, as we start to incorporate the very rare occasions where they might move to a spot and then back to their core area, as we move towards 100, that shoots way up. Okay. And there's different levels of core home range that are used. Sometimes it's the 50 percentile, sometimes it's 95%. Each of you may have your own kind of realm that you work within. The standard for reporting home range size differs. But this allows you to think about those across different what's referred to as home range levels. Okay, use all of the data. Of course, it will be the largest home range, and then as you start to subset the data, it becomes smaller and smaller. Okay, and home range calculations are notorious for needing a lot of observations. You need a lot of relocations, and if you think about the dates in this wild hog or wild boar data, they're out there every day or every other day. So it's really intense kind of following what these individuals are doing almost on a daily or every other day time step. Okay. But then the other thing that we can get out of that is a data frame that shows for each of those what's the value. Okay, and this by default is hectares. You can do question mark. If we go back to you can do question mark mcp.area if you wanted to report those home range areas in a different unit other than hectares. But here it is for the 20% home range level, and then all the way up to the 100 home range level. Okay, so you can pull those data from R if you're interested in thinking about comparing, in this case, home ranges of different individuals as recorded through time. Okay. So that's just kind of scratching the surface of what you might be able to do with home range estimations. That's mostly focusing on this idea of the minimum convex polygon. But I wanted to show you how to do it from starting with just raw XY data. Okay. And to do this, we're going to switch organisms. We're going to change to birds. So this Mitchell Gritz author has created on GitHub a data set from eBird. Those of you that think about bird data are probably familiar with this data set, eBird. If you're not, we'll take a peek at it today to think about it. But he has loaded some of those data onto GitHub. And to pull those data, we just need to run library read R, and then library, this is a library that he has created, MAGRITTR. We should be able to run this. And then run that library. Then the next line of code, we're just creating a URL file. And what I'm giving it is a URL link to GitHub where raw data, so it's raw.githubusercontent.com. Then we're going into the author that created this and stored this data. And we're going all the way down to ebird.csv. And so everyone should have access to this. If you run that, it'll create a URL file in your global environment here. Right now, it's just called URL file. The next bit of code, we're going to create an object called birds. We're going to do read_CSV. We're going to use the URL function nested within that to read that URL file that we just created, okay? And if that works, you should get an object in your environment called birds. So if I run that, it takes just a minute, but there's an object here called birds, 606 observations of 12 variables, okay? So in the past, I've shown you how to download packages from GitHub, but you can also grab data directly from GitHub. And so it's not only is it an R package repository, but it's a data repository. And sometimes there's data that have been stored on there that are useful. In this case, we're going to think about how we might define a home range of birds based on observations. So instead of telemetry data, where you're following an individual, that's probably the best way to get home range data. But you could use occurrence data to get an idea of core use where in this case, birds might occur, okay? So hopefully everyone was able to create this object called birds. If we click on that, it's a data frame, so we can view it. It has observation DT, which is just the date of the observation, the longitude, which is LNG, a name for the location, whether or not the observation is valid, so a true yes or no, the common name, whether or not the observation's been reviewed, the scientific name of the bird, so golden eagle in this case. I think this is location private, yes or no? Is it on private property? If there's someone that knows eBird data better than me. You might know what that means. It's not something we're going to be analyzing today. The number of individuals in that observation, the latitude, a unique location ID, and then an ID that incorporates the location, or sorry, that's the species. The species, the date, the time, and then the location ID. So putting a lot of stuff together in that last column, okay? And I know some of you are not interested in birds. I think birds are interesting, but we can focus on these data and pull just the latitude, or focus on the latitude and the longitude. Notice this is in a westerly direction, and think about occurrences or observations of each of these species, either through their scientific name or their common name, okay? And probably you will never pull data down like that unless you're doing some sort of meta-analysis, grabbing a bunch of data from eBird, in which case this next bit of code might be useful for you. But what we're going to do here is create a list of species from this raw data set that have at least 30 observations, okay? We're going to call this SPLST, that's short for species list. We're going to go into this birds object that we just created. So we got the % greater than, % meaning that within that data set, we're going to group, we use this function group by, where we group each of those rows by scientific name. And what that's doing is creating a chunk of data for each of the levels of scientific name. Then within those groups, we're going to summarize in, which is the number of observations. And we're just going to count how many times an observation was there. We're going to sum it. Then we're going to arrange it by n, so that we have these different values of observations, starting at the maximum number of observations and going down to the minimum number of observations. Then we're going to filter it so that we only keep those with n greater than 30, so more than 30 observations. Then, this is why we loaded the dplyr earlier, we're just going to select, for those that have observations greater than 30, we're going to select the scientific name, okay? Then we're going to use this extract to function to pull those scientific names out, and we're going to store them as a character, okay? There's a lot going on there, but the idea is to start with the whole database and then subset it so that we get down to just a list of scientific names for bird species that have at least 30 observations in the data set, okay? So what it's going to create is owner values here is an object called SPLST, and it should be the names, scientific names of birds that have 30 observations. Okay, so if you run that, now I have SPLST here. It's a list of characters 1 through 6. Here's the first name. I can just type it into SPLST. And what we have there is just a list of 6 names, scientific names of birds that have at least 30 observations, okay? If you're coming into this with your own data that you've collected, obviously you won't have to go through that process. And then we're just going to overwrite, meaning replace this object that we have up here that's called birds with 606 observations. We're going to overwrite that. So we're going to go into birds. We're going to filter that where we only have scientific names that occur within this object that we just created called species list. So it's going to go into birds. It's going to search through all of the scientific names. It's going to retain those that exist in this list of 6 species here. And then otherwise, it's going to drop all of the other names. Okay, and that's what that drop levels is doing at the end. Okay, and so when I run this, what I want you to notice is that birds goes from 606 observations to 435 observations. We still have all 12 variables, all 12 columns in there, but we've subset the data only to retain birds that have at least 30 observations, okay? So a little bit of processing there that you may not have to do if you come into this with your own data. But the output from that, we can plot this, is bird's longitude, bird's latitude, and then we're going to keep the ratio of that. And of course, because of my monitor here, let me just run that. There is a plot of longitude along the x. So of course, if you've thought about spatial data, we're starting at the prime meridian and moving west from there. And so this is in the western North America. And then we're starting at the equator and moving north from there along latitude, okay? And each of these points represents, in our case, an observation of a bird, okay? So this may be what your data look like. Of course, the nature of the data may be different. These may be relocations where you've plotted either individuals within a species or time steps of the same individuals within a population, for example. Okay, so that's just a way of taking these eBird data, getting them down into a data set that we might be interested in calculating home range for, okay? So the next bit is pretty critical for defining home range. When you are logging XY data, you may have XY coordinates coming off of a GPS that might be using like the North American datum from 1983. That might be the coordinate system that it's using to log those data, and it may be giving you latitude and longitude. And typically when we do an analysis, we want to project those data into a projection system that is a reasonable approximation for the part of the world that we're working in. And for those that don't think about spatial data a lot, just the take-home message is we're dealing with a globe. Hopefully there's no flat earthers watching this, because we have to think about the fact that these data are projected onto a globe, and we're taking those and laying them out onto a flat map or a flat area. And so to do that, there's obviously things change. And so projections are a way of us accounting for the fact that we're taking a globe and we're laying it flat. And then we're thinking about spatial relationships between, in our case, points. So we need to define the projection. And so the easiest way to do this, there's a lot of ways of defining projections, but we're going to create an object called PRJ. And then in a single quote here, we're doing this plus INIT equals EPSG colon, and then a 5-digit code that represents the UTM zone that we're working in, okay? Some of you, if you're coming into this with your own data, will already know the UTM zone that you're working in. If you don't, you can go to spatialreference.org and you can search for spatial data. So these example data that we're using on birds came from California. If we then went to a map of UTM zones, we could see that out there in California, it's UTM zone 11 north, so northern hemisphere. We're moving across to the 11th zone. And these data are based on the North American datum from 1983. If you plug that in at spatialreference.org, you will get an EPSG value that you can use in R to define your projection so that it is on a UTM grid for the appropriate zone that you're collecting data from, okay? And if it's more than one zone, you can either use the central zone or you can subset your data if you really need high precision of the data set, okay? There's a lot of projections out there. We don't have time to go into all of those, but if you're thinking spatially, you probably already have a good idea of the UTM zone that you're working in, okay? So we're gonna, I know this is like gobbledygook to those that have never thought about this stuff, but the way that I came up with that was to go to spatialreference.org, search for the zone that I was interested in, and then I found this 5-digit code that represents the projection in that region, okay? I'm sure there are other ways of doing that some of you may be familiar with. Alex, I know you're doing some of these analyses. You may be defining your projection using a different methodology, That's the thing about R. There's a number of ways to do the same thing, but for today's example, we'll just use this projection, okay? And if you want more information on that projection, you can use this capital CRS, and then in double quotations and real quotations, just put in that projection. And then it'll give you, it should give you information. If I can move this little window out of the way. It should give you information on that projection. Here, it's only telling me the same projection, but this is for UTM zone 11 north based on the North American datum 1983, and it's measured in meters. Okay, that's the, I'll have to go back and troubleshoot why it's not giving the exact details there, but you'll want to know what UTM zone you're working with. You want to confirm it, okay? So that little bit of code defining your projection is a pretty critical one. It's a source of a lot of heartache for those that are new to dealing with spatial data. But once you are able to define your projection, then creating a spatial points data frame, like this complex data frame that we're dealing with here that Alex was talking about earlier, the function is called spatial points data frame. And notice they're using camel caps, or the function uses camel caps to identify those different words. Okay, so we're going to create an object, spatial points data frame, SPDF. We're going to use the function spatial points data frame. We're going to use this argument coordinates and cbind, which is just column combine, birds, $longitude, birds, $latitude. Okay, then a comma, where those data are coming from, in this case, birds, and then the projection for stream, we're using the CRS argument on PRJ, that object that we just created up here on line 48, okay? This is probably the bottleneck for trying to analyze spatial data. Can you get it into the spatial points data frame and use the correct projection? Once you get over that hump, everything downstream of that is pretty straightforward, okay? So let's see if this is going to work today. You should get a new object, SPDF of formal class spatial points data set, okay? And once you, so you'll have, for your own data set, perhaps raw, lat, and long data, read it in as a spatial points data frame, define the projection, and then you can start going through either the minimum convex polygon examples like we did up above, or you can do kernel density estimates. And I know this is what at least some folks in the class are interested in, thinking about kernel, a dispersal kernel, and where a lot of the observations might occur on the landscape, okay? So in this case, we can use this function, kernel, capital U, capital D, and then we're just going to tell it that we want it to calculate kernel densities on this object that we just created, SPDF, and then create a kernel density for the fourth column. So I'm just going to type in down here, SPDF. If we get this window out of the way, we have a look at this. A lot of information. Right, so it's stored as this spatial points data frame, but there's the coordinates now together in a single column, and we've retained a lot of the original information that came out of eBirds. This is the observation date. This is the longitude. Then we've got location name. Is the observation valid? And if that is true, then we would want to include that in our measurements there, okay? So this little bit, using this fourth column here, is a way of including only the yeses for valid observations, okay? And my understanding is if there's someone questions the eBird observation, if it's not validated, then you you might not want to interpret that. Could be a misidentification, for example. Okay, so we're going to run this on this SPDF for valid observations, and it's going to create an object called KD. Okay, and then if we come back to this plotting window, we can plot an image of that. And now what we have across a grid is basically a heat map where white point represents high data intensity or high density of observations. And then as we fade from yellow into red, the density of observations is lower there. Okay, so kernel density estimation, we're thinking about where is the highest density of observations, in this case across the landscape. And let's plot that on our XY coordinates. Okay, so here's kernel density estimates, and this is across different species still, but there's a lot of observations in this area, a lot of observations in this area. Okay, and of course, if you're calculating home range, you'd want to be aware of these caveats in the data. Is there's spatial bias in data collection? Were searches happening everywhere, and they just happen to be high density here? Or is this just represent a high density of observations because it's a high density of searching? These are the things that you kind of need to know the ins and outs of your data and able to interpret this as a true either use of area or an area where a lot of observations are made. Okay. So then what we can do from this kernel density is draw in vertices that might represent home range based on some home range level. So 90% of the data. We might want to draw a circle around that, around the vertices of that. And what we can do is use this get vertices HR function on that KD object that we just made. We can define the level of home range that we want to use. We'll use 90 here, but you could change that. 50 is another one that you might see. And then we're using this add equals true again, just to plot those vertices on this map that we have here. Okay, so I'm going to run that, and what we get is a line drawn around the areas where where the 90th percentile of the observations. In our kernel density, at the heat map that we have, you can't really see the density of data that are shown here. But if we include the 90th percentile of the data, there is a cluster of observations that occurred in this circle here. Okay. Then we can create an object called UD. So all I'm doing is just taking this, and instead of adding it to the plot, we're just creating an object called UD. You can test the class of that. So this is a spatial polygon data frame. So now instead of points, we're thinking about polygons, and the circle that's drawn around there is a polygon. And then of course the beauty of that is that you can now plot those polygons. Okay. And typically when we're defining home range, we're thinking about what is the either relative use of different individuals or different species, or where do those home ranges fall on a landscape relative to a protected area, for example. So we kind of want to know in XY space or geographic space, where do those core ranges occur, those home ranges occur. So I showed you how to do it across all of the species. Of course, most of us that are ecologists usually think about a deeper level of taxonomic resolution beyond just birds. We usually think about at the species level. What we can do is we can create this kernel UD on this spatial points data frame and use the 7th column, which is the name of the species. You can run that, and then we can plot that. And so what this shows then is a kernel density where it's plotting it across each of the 6 species that had at least 30 observations. Okay, and so you can see some species really high observations in one area. Depending on your screen, you might see that there's a few observations there. This is just the default heat map that's shown. You could drill down into this image function and use different colors if there was a contrast that you like better. But now we can break it out by observations across these species. Okay. And we're almost to the bottom of the code here. what we can do then is just think about a particular species. So Cooper's hawk was a bird that I had heard of. I'm a fish guy, but so I don't know these data in and out as well as some of you might. But we can create this object, and I'm just using a code based on the genus and species. We can use the subset function on our spatial points data frame, where scientific name is absolutely equal to $2 this Accipitor cooperi, or however you pronounce it if you're a bird person. We can create a subset of the data where it's just that one species, and then we can go through, create the kernel density, and create an image from that. So there it is for just the one species. The true at the top represents we're only using valid observation. So valid observation, yes or no. We're only grabbing the trues out of there, and then we can draw the vertices around that and then plot those. And those would be the two main areas of use for that one species. And then, of course, sticking with the theme of plotting things across the lectures this semester using ggplot, we can load the ggplot2 library. We can use this fortify function where it grabs this object that we created when we made the vertices. It's going to take those polygons and fortify those. And then what you can do is ggplot, we can tell it AC, the object that we fortified. We can tell it our mapping aesthetics, where we want the X to be longitude, the Y to be latitude. And then because we have polygons, we can do geom_polygon, and it'll draw those polygons in ggplot. And we can set alpha equals to 0.4 just to give it some transparency. This would be useful if you were comparing different species or different time frames. If you wanted to see how those polygons overlap. And then there's this chord equal that will essentially make it a square plot where it's giving equal treatment to latitude and longitude. If you take this off, you get a plot that's wider than it is tall. But if you do chord underscore equal, it'll force those to basically be equal. And so what we get is this nice plot of the data that shows across latitude and longitude the home range area, in this case for Cooper's hawk. Okay. And then you may want to go on to plot base layers. There's a way of grabbing like Google imagery data. It used to be free, but now you can't just grab it. You have to create an account to get base layers. But you might want to, on the base of ggplot, you might want to plot a map, and then you could, on top of that, overlay these polygons for the home range. Or, as I've challenged you to do in the coding challenge here, what if you just created polygons for two different species and then looked at the degree to which those overlap? And if these were data collected through radio telemetry or relocations, that might be really useful for thinking about how much potential interaction between these two species might there be based on habitats used. Of course, the caveat here, we're dealing with observations from eBird, so there's some spatial bias probably in where observations were made, but still useful for the purposes of demonstration. So so I've asked you in your coding challenge here, can you use ggplot2 to make a comparison between Cooper's hawk home range and northern harrier home range? So if you're following along, in order to do that, you would need to create another subset for the species that you're interested in. You would need to create the kernel density, grab the vertices. Between the two species, you would want to use the same home range level. And then can you plot those two things together in ggplot? And I'll give you a hint. It requires taking this aesthetics argument and data argument out of the general ggplot and putting it into a geom polygon for each of those two data sets if you want to plot them together. And we've done that a bit this semester already. But I'll just hang out here until 1 o'clock or so if you guys want to work on that coding challenge, or if you want to discuss any of this. I know it's a lot. If you're not into spatial ecology, it might be way outside of your wheelhouse, but I know there's at least a few of you in the class that are interested in spatial ecology, so hopefully this was a helpful lecture.